In this lesson we're going to look at refraction and the critical angle and how this leads to a phenomenon called total internal reflection. So to do this we're going to use a semicircular glass block, and for example we're going to fire a laser beam at the centre of the glass block. Okay, let's do that. Now because this is a semicircle and we're firing at the centre of the glass block, the beam is not refracted as it passes across this surface, but it will be refracted when it leaves the surface. And we remember that according to Snell's law, when a beam of light passes from a high density medium to a low density medium, that's to say it passes from glass into air, then the angle of refraction will be greater than the angle of incidence. Right. So this is the angle of incidence and this is the angle of refraction. So according to Snell's law, when a beam of light passes from a high density medium into air, which we will assume has a refractive index of very, very nearly 1, so we'll call that 1, then we can say that the refractive index of the glass is equal to sine of r, the angle of refraction, divided by the sine of the angle of incidence. Now what happens as we increase this angle of incidence? Well, as the angle of incidence increases, then the angle of refraction will increase. So if we fire the beam here for example, then the beam will be refracted by a greater angle. But you'll notice that if we keep on increasing this angle of incidence, eventually we will get to a point where the beam is actually refracted directly along the boundary of the glass block, like that. Now we call this angle, when that happens, we call this angle here, that's that angle, we call this the critical angle. Let's make that clearer. So the critical angle is the angle of incidence at which the beam is refracted by exactly 90 degrees. That's to say, it's refracted along the boundary of the glass block. We call that C, critical angle, and the angle of refraction is 90 degrees. So rearranging Snell's law here, we'll write sine of the angle of incidence is equal to sine of the angle of refraction, n. Now then, at the critical angle, then the angle of incidence is called C, so we can say the sine of the critical angle is equal to, well, the angle of refraction is 90 degrees. That's to say the sine of 90 degrees divided by n, the refractive index of the glass. Now, you'll remember from maths that the sine of 90 degrees is equal to 1. So that simplifies the formula. We can say that the sine of the critical angle is equal to 1 divided by the refractive index of that material. Now what happens if the angle of incidence passes that critical angle? Well, for every angle of incidence that is greater than that critical angle, then the light will be 100% reflected. That's to say, none of the light will pass through this boundary, and we call this phenomenon total internal reflection. So above the critical angle we get a phenomenon called total internal reflection, commonly known as TIR. So let's just say for example that this block has a refractive index of 1.5, n equals 1.5. Then what would be the critical angle? Well, we write sine of C is equal to 1 divided by 1.5, which is equal to 0.6. So the critical angle would be the inverse sine of 0.66, which is equal to about 41 degrees. Yes, I do apologise that 41 degrees doesn't really correspond to the critical angle that I've depicted here, which is obviously a lot larger than that. But anyway, that's how you calculate the critical angle for a ray of light passing from a high density medium such as glass into air with a refractive index of 1. Now, the phenomenon of total internal reflection is very important in fibre optic communications. Now, optical fibres are normally made of glass or plastic, and they consist of a core with one refractive index and cladding with another refractive index. Now, because these have different refractive indexes, there will be a critical angle involved. Now, the thickness of the core is chosen such that whenever a ray of light passing down the core is incident on this boundary, its angle of incidence will always be greater than the critical angle. Now, as a result of that, the ray of light will be totally internally reflected. That's to say, it will be 100% reflected, and none of the light energy will pass across this boundary. It will be retained within the core as it passes along the fibre optic. So fibre optic communications can transmit light rays across very large distances with very small energy losses as a result of this total internal refraction that takes place within the fibre optic.